Okay, so let's start on lecture number 7. But before we do that, actually, I would like to go back to do something that I should have done, which I forgot to do last time, when we talked about energy in magnetic fields. And namely that I should have given the example that you find in my lecture notes. Namely that example. I'm not going to do the examples, to do the detailed calculations, but I just want to point out one thing which is interesting. Okay. In this example, let's consider a long coaxial cable consisting of two long cylindrical shells. Okay. And the inner one, then there's the outer one. Okay. On the surface of the inner shell flows current I, this direction. And on the surface of the outer, the bigger cylindrical shell, flows the current going back, that direction. And we are supposed to find what is the energy stored in a segment of length L. I'm sorry, my handwriting is getting worse. Of length L, let's say this much. An obvious way to do it is to apply what we derived last time, namely that the energy stored is nothing but the energy, the volume integration of B squared divided by 2 mu nu. Okay, so we have to find B for this cable, obviously. Okay, there's a magnetic field B in the region between the two cylindrical shells. And you can use Ampere's law, draw an Amperian loop to find out that the B field is circumferential. And you can calculate B. I would not take the time to do it. Something. Obviously, it's linearly proportional to the current I enclosed in this region. So it's I. And it's in the circumferential direction. All right? So to find the energy stored in a segment of length, then you only have to plug in this formula, 1/2 mu naught times the volume integral, for segment, for length of for segment of length L, times B squared. And that can be done. That is equal to something. Obviously it's proportional to the length L, and it is since it's B squared, so that would be give us a factor of I squared. It's like this. Exercise. Work this out. Work this out. And now comes an interesting point, which that's why I want to talk about this example. Namely that we can use this result for W to find the linear inductance for this coaxial cable. Because W is equal to half linear, the inductance of this self-inductance of this system, I squared. So that the inductance for length L would be given by this, and you cancel out I squared. and then you'll be able to find the self-inductance for this system. So this is a very neat way of calculating the inductance. So I should have, in fact, I forgot to talk about this example last time. All right, so now, let's start on lecture 7. And you remember that, we derived the boundary conditions, for the electric field and magnetic field E, on an interface between two homogeneous linear media. And the 4 boundary conditions are given here. We also, last time, derived, so, of course, we derived before, namely the energy density of the electromagnetic waves is given by this, and the Poynting vector is given by this expression, in vacuum. And the intensity, namely the average, by average I mean time averaged power of energy per unit area transported by the electromagnetic field is given by this simple formula, where E naught is the real amplitude of the electric field propagating. All right? And that we know that, the magnetic field B and E for a plane wave are both orthogonal to the direction of propagation. So those are transverse waves. And B also is perpendicular to E, and it is given by E. Total here implies a complexified the field. Namely, that I've used the cosine wave in a monochromatic wave, and promoted it to be the exponential function. All right, and remember that the magnetic B and electric E have different dimensions. In fact, the right thing to do here for in vacuum is, in fact, divide by speed of light in vacuum on the right hand side, because B has dimension of E divided by speed. All right. So now let's take these expressions, these 3 expressions. Maybe I can do it here. And write down the corresponding expressions. In a homogeneous linear medium. You remember, it's simple, because the Maxwell's equations for the vacuum case and the Maxwell's equations for the case of homogeneous linear medium differs only in the last equation, namely the equation involving curve B. And the only change is for vacuum, this factor epsilon naught mu naught is promoted to be epsilon mu, where epsilon mu are the permittivity and permeability of the linear medium. So that we only, for the case of homogeneous linear medium, for this, the corresponding equations would be obtained by, in fact, all you have to do is replace epsilon naught by epsilon. So now let me just use red pen. Linear medium. Homogeneous linear medium. Just erase the subscript naught in those 2 parameters. And, and for the expression for the intensity, all you have to do is, 2 things. Erase this and promote C which is the speed of propagation in vacuum, to be speed of propagation, v. Where v, as you recall, is nothing but the speed of light, c itself, divided by the index of refraction. All right? So that's all the changes we have to make. And now, okay, let's talk about, I'm done with this. So let me move this. Let's say that we have two homogeneous linear media. One on the left side and that one on the right side. So there's this medium 1, this medium 2 region. Okay. With index of refraction, okay, n1 and 2 respectively, and epsilon 1, epsilon mu1 for the permittivity and permeability in this region, and I have epsilon 2, mu2 in the second medium. So this is the interface, the boundary between these two regions. And let's say that we have a monochromatic plane wave coming in medium 1, hit this interface, and part of the wave will be reflected back in the medium 1, and part of it will be transmitted into medium 2. Okay, so we have, I have to write this, do this bigger. This coming in, this is an incident beam. Okay. The reflected beam, let me draw a normal here, and then part of it being transmitted in the signal. So this is the transmitted beam. Okay. And let's say that this interface is perpendicular to the direction x. So let me take this to be the x direction. And y and z plane will be perpendicular to this blackboard, perpendicular to x. And so, for the incoming beam, we have electric field EI, a vector, complexify it, that is given equal to its complex amplitude times for the incident beam, e to the I k I dot r minus omega I times time. And the corresponding magnitude B for the incoming beam is equal to, well, it's related to this, by, let's say, that's the 1 over C. Let's replace the 1 over V in the, oh, I forgot that you cannot see this. I was pointing out that B is related to E by this the unit vector of propagation cross E divided by speed of propagation. So like this, speed of propagation in medium 1 is V1. So that I now have K I vector that is stands for the unit vector along direction of propagation. Cross E I to the. And similarly, for the reflected beam, both of these two beams are in the same medium, so they have the same velocity of speed of propagation. We want so that let me use just red pen to write down the reflected. R stands for reflected, 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 reflected. V1 is the same, reflected, reflected. So this is the direction of the reflected beam. So it's K hat K R. And this direction is K hat I. And that, of course, I have the transmitted wave, and let me use green pen. So this is the unit vector is K sub T hat. And the electric field E for the transmitted wave is E transmitted or refracted given by E not transmitted, no I, be careful. This is not the T complexified E to the I K transmitted wave dot R minus omega T time. And the corresponding magnetic field for the transmitted wave is B sub T to the, and now it's equal to related to this, the electric field E by the factor 1 over speed of propagation. And now we're in the second medium, so that this is V2 for propagation speed in medium 2, and for medium 1, propagation speed is V1. So this is V2 unit vector along direction of propagation, K hat T cross E is the transmitted wave, like this. All right. Now, so we have to make use of the boundary conditions. Derived some time ago. And say, given here. So for all these equations, in those fields, electric field E and magnetic field B, you will have exponential expressions. The rest being amplitude, etc. So that in medium 1, you have contribution to the boundary condition from both the incident beam and the reflected beam. So that all those equations will be of the form. Let me write this down as this is something which will not in the exponential function. So that we have the exponential function will be either I K I dot R minus omega of I T for the incident beam, and then plus the contribution from the reflected beam, plus another factor not in the exponent, and multiplied by a similar looking exponential function, either I, k, and now we are talking about the reflected one. So in exponent is e to the I is I k reflected dot r minus omega sub rt. And those will be the two terms, on the left-hand side of the interface. And that would be equated to the corresponding thing in the right side in medium 2. So this is equal to, again, something multiplying the exponential function e to the I k. Now we are talking about the transmitted wave. So k sub t dot r minus omega r t. We'll come back very shortly to write down this, that, and that while in this bracket, this square bracket, and this curly bracket in a moment. But let's take a look at this. So that we want this coming from this or that to be equated to the corresponding thing in the second medium, which is this. At the interface, and let it set up the coordinate system such that the interface is at x equals 0. At x equals 0. All right? Right away, we notice that the only dependence on t appears here, here, and here. And they're supposed to be applicable for all time. So that the only way that this equality holds would be for omega I to be equal to omega r to be equal to omega, this transmitted t. So let me write that. Omega I have to be equal to omega r, got to be omega t. But you remember, that the frequency and the wave number are related. Remember, omega is equal to k times speed of propagation, v. So that we deduce that ki, v is the one in the first medium, v1, got to be equal to k sub r times the velocity is also v1. That got to be equal to k sub t for the transmitted wave times the speed of propagation. Now in the second medium, so speed is v2. And let's recall that v speed of propagation is c divided by the index of refraction. All right? From this equality, ki v1 is equal to kr v1, so we deduce that ki is equal to kr. So that the wave number for the instant beam is equal to the wave number of the reflected beam. And it's related to kT by a factor v2 divided by v1. Since speed of propagation is inversely proportional to the index of refraction, so this is also equal to k2 n1 over n2. All right, so much, So from now on, okay, I'm going to erase the subscript in omega. May I do that? Oh, no. This still got to be there. Sorry. Kiss of R. When there's no arrow on K, it's the magnitude. I can erase this. No, I can also erase the subscript. All right? Next, let's go back to this expression and look at the dependence on R. Appears here, here, and here for those three terms. Okay. And okay, this sum is equal to that at x equals 0. So we're interested at x equals 0. So that means that in fact, okay, we can replace this ki dot r by just the one, we can omit the one involving x with x equals 0. So let me in fact use the notation that k parallel means that those are the components parallel to the surface of to the interface. So this refers to if I take the direction perpendicular to the interface of x, so that the parallel components would be the yz components. So I only have to take a look at the parallel components. Parallel. So our parallel got two components, y and z. Parallel. There are parallel coordinates being arbitrary. This condition works for all points on the interface. So we deduce that k parallel for the incident beam is equal to k parallel for the reflected beam is equal to k parallel for the transmitted beam. Okay? So now, what I can essentially, I can now, make use. Okay, so I still some space here. So that, after having used this condition for the boundary condition, we have concentrated so far on the exponential factor. And let's see. So at this point, let's notice that, so we have the x direction here, which is the perpendicular direction. And then we have the parallel components of k on this. So then let's talk about the plane formed by the x vector and the parallel k vector. And we call that plane to be plane of incidence. So now, this is a plane of incidence. So it's a plane. All the three beams lies on this plane. And let me adopt the coordinates such that let's say that in fact this plane of instance is the plane formed by the x-axis and the y-axis. So take this y. And now let me also draw note down the angle of incidence. The angle of incidence is the angle made between the normal to the surface, to the interface, and the direction of the incoming beam. So let me call this theta sub I, and this angle to be theta sub R, angle of reflection, and this one to be theta sub T. Notice that the angles are defined by the beam and the normal, not the interface. Make sure you remember that. All right. So what else? I can let's see. Oh, okay. We now take a look at this equation, and the parallel components, of course, now lie on this plane, and so that let me. What do I want? This this is a simple thing, but why do I have a problem? Okay. What should I be looking at? Oh, let me also. Oh, okay. Let me come back here and let me. Okay, so this is k vector reflected with a vector, and this for transmitted for this one. And let me look at the one among the parallel components, you have y components and z components. Okay, and z component of course is 0 because this is the plane of incidence. This everything lies on the x y plane, so that this now boils down to the requirement that this y component of reflected beam and y component of the wave vector for the incident beam and y component of this got to be equal. The y component of this beam would be ki times sine, right? Sine, so ki magnitude of the wave number, times sine theta I, got to be equal to this component along the y direction, which is kr times sine theta sub r. And this one, the y component of the wave vector is given by kt times sine of theta t. All right. From this, we deduce two pieces of information. Remember the ki is equal to ri. Ki is equal to kr. I'm sorry. So this is equal to that. That means that sine theta I is equal to sine theta r. That means that the angle of incidence is equal to the reflected angle. So this angle is the same as this angle. Furthermore, so ki sine theta I is equal to kt sine theta t. So we have this ki over kt. If I put this to the other side and put this on the side, is equal to sine theta t divided by sine theta I. But we already know that this is not true. This KT. But we already know that okay, Ki over KT, so if I put this to the last side, Ki over KT is N1 over N2. So that the angle of transmission and the angle of incidence are related by the two indices of refraction. Thus, equality is known as Snell's law. And we may have use for this later on. So let me save this. All right, this, I think everyone knows. Angle of incidence is same as angle of reflection. So I do not have to keep it, we know this. All right, so now what's next? Okay, and now we are ready to do some real calculation. Let's now consider the case that, did polarizations of the beams lies on the plane of incidence. And, of course, the polarization vector is determined by E, the electric field E. So let's ask, now, should I use, or maybe I should use, So this is the direction propagation. So if I take this, to be the direction of the incoming electric field E, which of course is perpendicular to this direction. And then the B field would be, B is in direction of propagation, cross this one. So the B field, B I, would be out of the blackboard. So this denotes out of the blackboard, perpendicular to both E, I, and Ki. And let me also draw the electric field E for the transmitter beam. Got to be perpendicular to this. So let this take this to be that. So this is E, T vector complexified. And the corresponding magnetic field B would be given by B is K cross E, so it's out. So B, T is out, perpendicular to this plane. And for the reflected beam, let me take this to the direction of E R, perpendicular to it. The important thing is that it got to be perpendicular to it. Direction of propagation. In that case, B will be K cross K cross E will be into the black, into E R, into the black. So all the electric fields vectors are on the plane of incidence, XY plane, and all the magnetic field B's been perpendicular to the incident beams. Let's talk about that case. And in the homework, you'll be asked to consider the case that the polarization being instead of lying on the plane of incidence, being perpendicular okay, to the plane of incidence. But in fact, okay, this case I'm talking about is a more interesting one and a slightly more complicated one. That's why you find out. And okay, next, so let us okay, also okay, work out the angle. So this is okay, the angle of incidence plus this is 90 degrees. So this is okay, theta I. This is theta R. So this and this. So this angle is equal to this angle. Okay. So this angle must be okay, the angle. This is R. This and these two are parallel. This equal to this one. This is complement of this one. This is complement. So this correct. This is okay, theta I, 30. So this okay, we know that this angle and this angle are equal, and this angle is complement okay, of 30. So this must be 30. That. And let me catch my breath, and also take a look at my note where I am. Make sure that I do not okay, omit anything interesting. Okay, I think I've covered everything so far that I want to cover. All right, we can proceed from here. And let me make use of the slide in the report. And I hope I do not use any of this anymore in this lecture. But if we do, then I just take it. Okay, I'll put down those equations that I need. So let me erase them. All right. Sounds nice. Oh, did I erase? Oh, my goodness. What? I erased the boundary conditions. Oh, that's what I did. Oh boy. Okay, let me get boundary conditions. There are 4 of them. Okay, first one. Oh, well, in order to make sure that I do not make stupid mistakes. Okay, so epsilon 1, E1 perpendicular is equal to epsilon 2, E2 perpendicular. Of course, B1 perpendicular is equal to B2 perpendicular. And that E1 parallel. Parallel, of course, consists of 2 components, the y and z components. So it's a vector. So, and E2 parallel. And then finally, I have 1 over mu 1 B1 parallel vector is equal to 1 over mu 2 B2 parallel. I thought I have it written down here, but no. Okay, let's keep this in. You remember that, okay, in each of these, there are terms involving certain thing multiplied by an exponential function. Okay, and now we have taken care of the exponential function. They are all equal, so as to derive all these results. Then what's left behind? Not the things not in the exponential function got to be equal. All right. So let's see. So we want this equation perpendicular. Perpendicular is in the x direction. So epsilon 1, in the first region, you have, the electric field E from the incident beam is this, this x. plus E, okay, R, the x component is equal to epsilon 2, okay, E, okay, transmitted, okay, along the x direction. And this one is just, okay, B, I, okay, in the x component is equal to B, I'm sorry, of course, they reflect the B mass plus B plus B R x component is equal to, that's the, this one, equal to B2 is transmitted, from the component is just x component. And now we have, okay, the more complicated one, namely the, okay, the one involving y and z components. And this one is, okay, y I plus, EI plus E R, okay, the y and z component, and that's equal to E T, okay, for the y and z component. And finally, we have this one of the mu 1, okay, B I plus B reflected, okay, the pair components y z component is equal to the cos 1 over mu 2 B T, the y and z component. Okay, so that I want to make sure that I've covered down everything correctly. Okay. Oh, as I expected. Okay, remember that. Okay, all those fields consist of something times the exponential function. But the thing that's multiplying the exponential function refers to the amplitude. So in fact, okay, so in those expressions, in fact, we have talked about, okay, the amplitude. Amplitude, of course, is given by, okay, subscript 0. And we're still talking about the complexified expression. Okay, so 0, 0, 0, 0. All complexified. 0, 0, 0, 0, 0, 0. That's it. I think I've done things properly. Okay. So we have to obtain these 4 equations for the case we are talking about: incident beam in, reflected beam, and then transmitted beam. The left side refers to what happens on the left-hand side, and the right side here refers to the transmitted beam on the right. Okay, let's write down those requirements. Or this 0. Okay, thus, x component of EI is this one, x component goes this direction, but EI points that direction. So it's, so this gives me epsilon 1 minus, since the x component points away from the x direction, and this EI, is E naught do we want to carry those? Not all of them. Yes. Okay, let me be consistent with my notes. Yes, let's do that. Okay. The x component is this direction. So it's times sine theta I. The next one, is this, the x, the y, the x component is, which is along this one, so it's plus ER, not complexified. I see this, so that one that, so there's cosine of this one, cosine of this angle is sine of the complementary angle. This, so sine theta r. The right hand side, the left hand side of this one, this is equal to epsilon 2 times the transmitted beam is this one, and okay, ET is this, and I want the x component. X component is in the opposite direction, so that's a minus sign times minus sign, and along this direction, so it will be sine theta t. So that's that equation. And then this equation is simple. So we want to equate the x components of the b's. But as I said, okay, b only has non-zero component in the z direction. So it's no y direction component, no x component. So this is simple. This is nothing but 0 equals 0. That's one. All right. This one. Along YZ direction. So what's that? YZ. Well, the z component is simple because all the fields lie along on the xy plane. So this we can forget about the z component. Equation corresponding to the z component. So just concentrate on y. So this the y component of EI is this direction. So it is this times cosine that. E0I complexified cosine. Oh, now that I've used oh, that's okay. I've forgotten this being E forgot this E not transmitted. And this one is oh, I was looking at the EI, the Y, come on. So this, so it is times cosine of theta I plus this one direction also multiplied by cosine. So E dot I R times cosine of this angle, but the reflected angle is equal to this angle. So in fact, I may as well pull this out. Sine theta, oh sorry, cosine rather. Y direction, right? Cosine of theta I, and that's equal to all of them. This one, so it is 0 E0 P complexified times cosine theta of the transmitted angle. That. Finally, this equation, and obviously, as we said, z the manifold B event is perpendicular to this plane of instance, the xy plane. So I ignore this y component equation. And okay, so I have B not I is out of the black box is plus Z, but this is minus Z, goes into this. So I have 1 over mu 1 B 0 I is plus, but for the reflected beam is down, so it's minus B 0 R amplitude, and that's equal to 1 over mu 2, and the magnitude B for the transmitted wave is out also, so it's plus, so it's B 0 T compass right. And before I solve the equation, let me check with my notes to make sure that I have not missed any factors or things like that. So that I have. First equation is epsilon 1 minus the sine right. So this and this one is cosine right, cosine plus, and that's equal cosine of this, correct? And finally, I have a mu naught, Oh, I'm sorry. The magnitude, of B, of course, as you recall, is related to the magnitude of E divided by the speed of propagation. So let me, in fact, replace this, if I may. So this is in the first region. So let me replace this by E divided by V1. Luckily, may I just erase this? So, well, let me change this to 1 over mu 1 V1, then I have E to the 0I minus E not R, and that's equal to 1 over mu 2 in the second medium now. So B is related to E by this factor of V2. That should be right, correct now. Let me check. Correct. All right. So let me solve these 4 equations. I mean 3 equations. This one, and this one. And let me use the parallel bracket in case I need some of those things. Okay. All right. So let us solve this equation. And this, the 2 angles are equal, so that I have this, multiplied by minus, plus, minus. So I have, and this, let me go to the other side, so that I have E naught I minus 2 E naught R that's equal to epsilon 2 divided by epsilon 1, and that sine theta t divided by sine of theta I. And you remember, Okay, Snell's law. Okay, so Snell's law is this, if this is n1 over n2. So n1 over n2. And in fact, okay, you can also rewrite that as follows. So this is equal to n1 and n2, but this is also equal to n is inversely proportional speed propagation is equal to v2 over v1. So let me write that as v2 over v1. And then what else? Oh. Okay. And then times E not T. Okay. Let me erase this so as not to confuse ourselves. Next, this equation. Okay, so that and then let me take a look at this equation. This equation also involves the difference between the incident beam and reflected beam. So this is also equal to put this to the other side. mu1 v1 over mu2 v2. v2. E not T to the. So this is taken care of. This taken care of. And then finally, we have this equation, which says that B not I minus B not R is equal to mu1 over mu2, B. Oh, I'm sorry. I should not be looking at this one. I should look at this one. Sorry. We have rewritten this already. Let me cross it out. Not the confuse me. So we have E not I to do minus E not R to do is equal to. Oh, I'm sorry. I've written down this already. So I should be looking at this equation. The last one. So I have E not I to do plus E not R to do, and that's equal to this, and that is cosine theta transmission divided by cosine of the incident beam. Times E not T. And since I've been making algebraic mistakes, and you guys are not here to help me out, to point out my mistakes, let me compare my lecture notes to make sure I've done things properly. So this one is that. Okay, so let's call this by something. Let me call it beta. And I have to show that in fact this is equal to that. I will do that in a moment. So that is okay. So this one is E1. Oh, correct. Okay. So this presumably, in that case, got to be equal to that. We'll show that in a moment. But let me check this one. This is plus that. Right. Okay. Let me call this ratio to be alpha. So I've introduced alpha, give me that, this equal that. So let me, in fact, show that this equal to that. This is equal to that. And let me okay, do this, okay, so that, okay, I start with epsilon 2 V2 divided by epsilon 1 V1, this beta, yeah, and I want to show that you that. To do that, all I have to do is multiply both, okay, here by, okay, mu 2, then divided by mu 2. And here, multiply by, okay, mu 1, then divided by mu 1. The reason I'm doing this is that, okay, remember, epsilon mu, the product, is given by 1 over speed of propagation squared. So that this, okay, is equal to 1 over V2 squared, but the V2 cancel with this one. Okay. So that, okay, I have just one left. And then there is this, okay, mu 2 there. Similarly, okay, epsilon 1 mu 1 is, okay, 1 over V2 square, okay, I'm sorry, V1 square, or one of that, okay. Okay, so this is nothing but 1 over V1 square. It's in the denominator. One, the V1 cancel with this V1 is in the numerator denominator, so it got to be promoted to be, okay, V upstairs, so V1 upstairs, and then this V1. So the beta given this is equal to, yes, V1 mu 1 over V2 mu 2. Okay? So, okay, let me in fact copy that down here somewhere, because I will need that in a moment. Beta is equal to epsilon 2 V2 over epsilon 1 V1, and it's also equal to mu 1 V1 over mu 2 V2. And, okay, let me rewrite the second one as, okay, instead of V1 over V2, okay, I can write it down as, okay, the ratio of, okay, indices of refraction. So this is here mu 1 over mu 2. V1 over V2 is nothing but N2 over N1. So beta is equal to this, and they also can be written as this. And we will have use for this. 2, okay, expressions in a moment. So I'm done with this. Let me, to save space, let me erase this. So that now, okay, I have two equations to solve. Okay, this is now beta. This is alpha. So we have two equations relating those, okay, amplitudes for the electric field E. And now, okay, if I take the sum of these two equations, this term cancels with this term, so this plus that, so that, okay, I will have, okay, E not the transmission one equal to this plus that cancel out, so there will be 2 of this. So 2 times E not I divided by, okay, this plus that's alpha plus beta. On the other hand, okay, I can, so I've, okay, written, okay, the transmitted amplitude related to the incident amplitude. Let me, okay, do not, okay, to write, okay, the reflected, okay, amplitude in terms of the, okay, incident, okay, amplitude. So the way to do it is this minus that, okay, then they will get twice this, and this cancels. So that I have E not R, this minus that is 2, is equal to this minus that. So it's alpha minus beta times E naught t. This minus that, alpha minus beta, right? So that the 2 goes to that side, 2. But now I know that the transmitted amplitude is given here. So this is equal to this minus times that. The 2 cancels. So that I have alpha over minus beta over alpha plus beta. Alpha. Right. So this transmit. So this one. Okay, this times this cancels, right? And then I have just this left, E naught R. So that, okay, in terms of the incident amplitude, the transmitted amplitude, and the reflected amplitude are given by these 2 equations. Let me erase this. This pair of equations is known as Fresnel's equation. Did I spell it right? Fresnel's equations. And I did not. Okay, they reflected in this. Right, correct. Now let's take a look. Oh boy. Well, we have to finish the calculation next time. But let me start here. So we have now these 2 equations. And let's take a look now at alpha and beta. Alpha is, beta is given here. Alpha is, where am I? Just erase this. Alpha is just the ratio of the cosines, which I managed to erase. So this beta, alpha, is equal to cosine of the ratio of cosines is the transmitted versus cosine theta t over cosine theta I. Somehow I forgot that. I just by mistake erased those equations. All right. Let's notice that alpha and beta are real quantities, and in fact they are non-negative. And now, let me go back. Take a look at the expression for alpha. So alpha is equal to cosine theta t divided by cosine theta I. Let me square both sides. So this is alpha squared is equal to cosine squared. Cosine squared is 1 minus sine squared. Let me keep this for a moment, cosine theta I, like this. In a moment. Square. Well, in fact, let me not square. Take square root. But remember, sine theta is related to sine theta t is given by, in terms of sine theta I. Okay, this one T is so related to that by T is in the second medium. Okay, so it's N 1 over N2. Because, okay, this the ratio is inversely proportional to the index. That's right. Okay. So that okay, I can change that to okay, sin theta square I times okay, N 1 over N2 square. Let me point out two things at this time. Namely, the alpha is inversely proportional to cosine theta I. So that, but cosine theta can be 0 at 90 degrees. So let me talk about the case that cosine theta I is 90 degrees. Then this is 0. Then alpha diverges. What does that mean? Let's see. Okay. Alpha diverges. Okay. That means that event, okay, that's infinity, so that the transmitted beam is 0. Alpha is large, so this is 1. So the reflected beam is equal to that's okay, the transmitted, the incident beam. So that okay, the whole beam being completely reflected. Okay, and there's no transmission. And some of you might have already encountered this phenomenon, namely that if you drive in a rainy day, okay, the ground's wet, you got very bad reflected beam coming towards you. All right? Next, the more important interesting thing is that, okay, let me take a look at this equation. Namely that, remember I said that alpha and beta both okay, real and okay, non-negative. So notice that okay, if when alpha is equal to beta, then okay, the reflected beam is completely okay, extinguished. So that okay, we have okay, when okay, is 0, okay, when okay, alpha is equal to beta. Okay, now let's okay, see when do we have okay, at what angle of incidence would we realize this equality alpha equals beta. Alpha is that, alpha is this, okay. So that okay, I want this okay, alpha equals beta, so the alpha square will be equal to beta square. Alpha square is this square, so there's 1 minus sine theta I times n1 over n2 square divided by cosine square can be written as 1 minus sine square, 1 minus sine square theta, that's square okay, of theta I. And that okay, is alpha square is equal to beta square. When this happens, okay, we call that angle, this is the angle, okay, named after someone called Brewster. Okay. When this is low, then angle is called the Brewster's angle with subsequent beta, B. So this is the Brewster's angle. Okay. When the incident beam comes at this angle, okay, then you have okay, complete extinguishing of the reflected beam. And okay, at this point, let me in fact take a look at beta, expression for beta. Beta is okay, given by this. Okay, beta is okay, mu1 over mu2 n2 over n1. Okay, But okay, the permeability for most media are very comparable, they're equal. So that as a first approximation, okay, we'll set this to be 1. So the beta is equal to n1 over n2. So that here I can replace this n1 over n2, n1 over n2 to be 1 over beta squared. And now you can solve this. So when the angle is the Brewster's angle, so theta I is theta B. I will leave it as an exercise. Okay, since I've been making so many calculational mistakes, so I better not do it in class. All right? Okay, let me leave it as an exercise for you. Okay, so this is now beta squared, 1 over beta squared. Okay, exercise. Show that you can solve for the Brewster's angle, and is equal to tangent of the Brewster angle is n2 over n1. And if you are talking about the case, okay, the incident beam comes from air towards the interface with this being water. Okay, we note the indices of reflection of air being roughly 1, and for water is roughly 1.5. Then for that case, you will find out that the Brewster angle, it will be roughly 57 degrees from air to water. Let's stop here and continue, okay, the discussion in the next lecture.